Okay, welcome back. In our last lecture, we talked about what a non-interference policy is, and I described non-interference to you a little bit. We're going to talk a little bit more about non-interference today. Right. So imagine you have a very simple confidentiality scenario in which you have a high-level domain and a low-level domain, or you could imagine a high-level subject and a low-level subject, right? So recall that in that scenario in MLS, what we wanted was for information not to flow from high to low. It's okay for information to flow from low to high. And so in the non-interference version of that, our policy is very simple. We just say that L is allowed to interfere with H. And allowed to interfere with, if you recall, means that information can flow from L to H. And since we didn't say that information could flow from H to L, then that's precluded. Okay, so notice that, very simple policy. It matches very closely what we said was the meta policy for this system. And we didn't have to worry about things like who can read what and who can write what, as we did in Bell and LaPadula. All right, so the non-interference policy is very abstract, but we're left with the question of how one would implement a system like this, or if you had a system, how you would verify that the system actually satisfies this non-interference policy. With Bell and LaPadula, it's pretty clear how to implement the policy. You have these rules in place, and you have some software module that says yes or no when a subject requests access to an object. And you could look at that system and verify, by inspection or by some proof, that the system in fact satisfied the Bell and LaPadula rules. But for non-interference, you have a much more abstract policy. So how would you go about doing that? Well, think about it this way. If our policy says that information can't flow from H to L, but can flow vice versa, then recall earlier we said that it shouldn't be the case that H can do things, the effects of which are visible to L. Because if H can do things and L can see the results, then they can use that as a mechanism to send information. And so that's really what we want to show about the system. Okay, so imagine you have a system on which H and L are running either concurrently or in some interleaved fashion. Well, they're both going to be performing operations. And so imagine you have this sequence of interleaved operations where L takes a step, and then L takes another step, and then H takes a step, and L takes a step, and so on, right? So you could represent that as a sequence of instructions performed by the two subjects. Now, what should be true at the end of the day after you run this system from L's perspective? Well, supposedly H was not supposed to be able to do anything which L could see. And so if you took that same sequence of instructions and threw out all of the operations that were executed on behalf of H, L shouldn't be able to tell the difference. And so we have here two sequences of instructions, and the execution of those two sequences on our system model should look identical from the perspective of L. That's the key to this. And if we could prove that that was true for arbitrary sequences of instructions and arbitrary interleavings, then we could infer that there was nothing H could do that would be visible to L. Because if there was something H could do which was visible to L, then there would have to be a sequence of instructions which would manifest that effect. Okay, so that leaves us with one final question, and that is this. What is it that's within L's view of the world? Right? The view has to be the same in those two executions, but what does view mean? Well, that's where we can play with our model of the system, because if view of the system means only the contents of files, well, that's pretty much what Bell and LaPadula was about, right? And if view includes the values of system attributes and system flags, then that's where the covert channels come in. And if we can prove that H can't do anything which will affect those in a way that L can see, then we don't have any storage covert channels. If we throw into our view the clocks and the interleaving or the ordering of events, then we can't have any timing channels. And in fact, if we threw in everything that L could possibly see, then there couldn't be anything that H would do that would send information to L. Well, it seemed like a no-brainer. Why don't we just do that? Well, the answer is that in realistic systems, there really are lots of interferences. And so if you made the view that inclusive, it would be impossible for most real systems to ever prove that it was non-interfering. Another problem is that most of those attributes of the system which might be manipulated in covert channels are very low-level attributes, way down in the implementation. And so if we were going to prove that our system was non-interfering, then we'd have to have a model of the system at that very low level of abstraction, and that's hard to come by. And finally, there are many interferences in realistic systems which are benign. For example, if a high-level subject encrypts a file and then puts it out into the common file system, say, that is an interference, even though the low-level subject can't read anything about the contents of the file because it's encrypted. And so there may be cases in which we want to say, well, that sort of thing is okay because the low-level subject is not really getting any information, even though that mechanism could be used as a covert channel. Okay, so what have we learned? Well, non-interference is a very expressive, a very abstract policy that's good in a lot of cases. And there are ways in which we could establish that a system satisfies non-interference by proving this thing about the arbitrary interleaving of operations by subjects. But it turns out that that's really hard in realistic systems because most realistic systems have a lot of potential interferences. Thank you.